In our everyday intuition, infinity is a featureless void, an unreachable, abstract horizon. We experience it as the place where counting simply stops. Standard calculus classes teach infinity as a concept of unboundedness. It's a way to describe a function that increases without end, rather than a tangible value you can manipulate in an equation. By the late 19th century, this vague definition lacked the precision needed for advanced logic. Mathematicians required a rigorous way to map the physical continuum, which meant they had to move past treating the infinite as a blurry forever. Georg Cantor broke this stalemate by treating actual infinity as a completed, quantifiable object. He realized the infinite could be analyzed with the same mathematical certainty as the number 5. To cross this boundary, we have to realize that position, size, and arithmetic split into 3 distinct mathematical categories the moment we leave the finite world behind. First, we have position. We count sequentially, 1, 2, 3, moving tick by tick along the line of natural integers toward forever. Cantor defined the very first transfinite position as omega. This single point represents the completion of the entire set of natural numbers. Because omega is a well-ordered position, the sequence continues. We can step past it to reach omega plus 1, omega plus 2, and so on. This ordinal counting scales exponentially. We eventually reach omega times 2, representing 2 consecutive infinities, and can continue all the way to omega to the power of omega. Ordinal numbers provide a navigation system to pinpoint specific addresses located infinitely far past the end of the standard number line. This counting raises a question of scale. Does the position omega plus 1 possess a larger total size than omega? In terms of raw size, measured by cardinal numbers, adding 1 to infinity changes nothing. Every element in these 2 sets can be paired up perfectly. This shared size is a transfinite cardinal called Aleph naught. However, Cantor's diagonal argument proved that the set of all real numbers, the decimals and fractions, is infinitely denser than the set of integers. The 2 groups cannot be paired 1-to-1. This establishes a definitive hierarchy of transfinite sizes. By taking the power set of existing collections, we generate an endless sequence of larger infinities, moving from Aleph naught to Aleph 1 and beyond. Cardinal numbers reveal a nested hierarchy of definitively larger infinite masses, each one dwarfing the quantity that came before it. Beyond position and size, we need a way to perform algebra. We need a system that allows us to add, subtract, and divide these infinite values directly. These algebraic rules were unlocked through the development of surreal and hyperreal numbers. John Conway pioneered the surreal numbers while researching the endgame logic of the board game Go. Surreal fields treat infinity as a genuine number on an extended line. This allows for precise calculations, such as dividing infinity by 2 or subtracting exactly 1 from it. Dividing 1 by an infinite value generates an infinitesimal, a precise number smaller than any real fraction, but strictly greater than 0. Surreal fields demonstrate that the same algebraic laws governing finite numbers apply perfectly to infinite and infinitesimal values. Crossing the infinite boundary reveals a landscape of consistent logic and rigorous structure. We now possess 3 distinct tracks: ordinals for sequence, cardinals for size, and surreals for exact algebraic scale. The transfer principle ensures this logical stability. It states that any first-order mathematical truth found in our standard finite numbers remains true within the hyperreal transfinite system. Crossing this local boundary of infinity no longer leads into an empty void, but reveals a vast, limitless, and entirely calculable beginning.